So often we have a nice and symmetrical distribution that looks like this. I will call that the normal distribution, the bell curve. And we've seen that the mean, and in a situation like this, the mean, the median, and the mode would all agree, or pretty much agree, with each other. And the standard deviation on top of that gives me an indication of how the values are spread around the mean. Do I expect values to deviate a lot or just a little bit? The standard deviation will give me an indication of that. So if I, for example, have a score of, so in this case my mean is 20, my standard deviation is 3. But what does that 3 really mean? What does that 3 mean? What does the 3 imply? If I have a score from a specific person of, let's say, 26, what does that really mean? If this comes from a leadership test and I get a score of 26, does that mean the person is a good leader? And how good? How close is that 26 to the average? Well, the average in this case is 20, and the standard deviation is 3. So that 26 sits 2 standard deviation steps from the mean. Now in this bell-shaped curve, we can say a little bit more about that score. So if I know the standard deviation, it can tell me how much above or below, by how much does that score differ above or below the mean. So let me just think of what I want to say here. So in this just introduction example, I can see the standard deviation as sort of a unit of measurement. It sits 2 standard deviation units from the mean. So I can use the standard deviation to measure distance from the mean when I have this normal distribution, this bell shape. Let's go to the next example. So if I have some sort of rating for a person's planning ability, whatever that survey may be, and I get a value of 84. Now in this distribution, the mean, the average is 90, and the standard deviation is 12. If I have a score from a person of 84, how good or bad is that? I can't necessarily just compare 84 to 90. Is that a big difference or not? The standard deviation tells me how far away that is from the mean. So one standard deviation unit is a score difference of 12. And if I have an 84, I think my example is, if I have an 84, that is a difference of 6 below the mean. So it's half a standard deviation step below the mean. So even though the actual number difference seems maybe high, it depends on the variability by way of the standard deviation. That tells me how bad that score actually is. An 84 versus a 90 isn't that bad when the standard deviation is 12. It's only half a standard deviation step below the mean. Whereas in my previous example, I was dealing with slightly different numbers, and there the difference was 6 from 20 to 26. So still a 6 difference. But it was much, the 26 score was much better, was much further away when I measure it in standard deviation steps. So it's not just the number and the mean, but the standard deviation tells me it gives me a way to measure distance from the mean. The number of standard deviation steps, half a step to the left, or in the other example, 2 steps to the right, I am going to call the z-score. So with the z-score, I'm going to count the number of standard deviation steps away from the mean. So with this situation, I have a mean of 90, standard deviation of 12. A mean of 90, standard deviation of 12. So I'm taking steps of 12 from 90. So 1 step is going to put me at 102, and the corresponding z-score is going to be 1. 1 step, 1 standard deviation step. Another step is going to put me at 114, which corresponds to a z-score of 2. I took 2 standard deviation steps. If I took steps to the left, away from the mean, then I'll have negative scores, indicating moving to the left. So my score of 84 puts me half a standard deviation step from the mean to the left, which corresponds to a z-score of negative 0.5. If I took a step of 12, which is 1 standard deviation to the left, the z-score indicates I took 1 step to the left. 2 steps, 3 steps. So it gives me a way to sort of standardize the numbers, that regardless if I'm working in the 90s, the z-score tells me 0, 1, 2, negative 1, 2, in terms of steps away from the mean. Whether I look at numbers like that, or numbers around 20, with the property of the distribution, I simply refer to the distance away from the mean in terms of standard deviation steps. So in this case, the standard deviation is smaller, so it takes steps of 3, and that's 1 standard deviation step, 2 standard deviation steps, and negative in the other direction. So the z-score is a way of standardizing the distribution. So if I look at this, how do I calculate the z-score? So I take the raw score, the original values, and convert them to their corresponding z-score by way of this formula. I don't want to reveal too much, so it's a little low. Hopefully everyone can see it. So how do I calculate, given the mean and standard deviation and a specific score, how do I calculate its z-score, indicating where it actually sits in the distribution? This is how I take the difference between the score and the mean and divide by the standard deviation. For example, if I have my 84 example, where does that actually sit in my distribution in terms of standard deviation units? The z-score tells me that. 84 minus 90 gives me a negative 6. Now I'm just standardizing that negative 6, dividing it by the standard deviation, giving me a negative 1/2, meaning that I took half a standard deviation step to the left. If I look at the previous example, the leadership one, now I was working with 20, and I had a score of 26. So I take 26 as my actual score minus the mean of 20. So that puts me a distance of 6. But how much is that in standard deviation units? Divide by the standard deviation of 3, and it tells me it was 2 standard deviation steps away. So even though in terms of the raw score, the difference was 6 in both cases, 20 to 26, and the other example was 90 to 84, they are very different positions in the distribution. a score of 26 here is a very good score. It's 2 standard deviation steps away. And in general, with this normal curve, 1 standard deviation step in either side cover around 65% of everything that I'll see. If I go another standard deviation step in either direction, that's around 95% of all my observations will be covered by that. So if I have a score of 26, the z-score indicates how good that actually is. 2 standard deviation steps away is pretty good. Whereas in this one, nah, it's pretty average. Yes, the distance might seem like the same in 6, but if I calculate the z-score, it's only half a step to the left. So it's a little below average, but not much. Not much. The z-score, sort of the standardized scores, give me a way to easily see where the actual score sits in relation to the distribution. Any questions on that? Z-scores.
So Z is always like 0, 1, 2, 3.
Yeah. It measures, it counts standard deviation steps from the mean. So regardless of my numbers, regardless of what the mean is, 115, doesn't matter. I just take these numbers and sort of standardize them. And then it's easier to compare completely different scores, completely different sets of numbers, but a similar distribution. I can say which one's good and which one's bad by looking at the standardized scores.
Question.
Yeah.
Why do you divide -6 by the standard deviation?
So if this is my 84, so the distance in terms of the actual score numbers is a 6. What the z-score wants to measure is how many standard deviation steps did I move. Now, 1 standard deviation step is 12 units. I moved a distance of 6, so that's half a standard deviation step. So by dividing by the standard deviation step, by dividing by the standard deviation, I'm converting it into steps instead of the actual distance. Same for this one. Which was the first? This was the second one. So, same for this one. There I have a distance that I sort of traveled. The distance is 6, but 1 standard deviation step is 3. So I took 2 steps. 6 divided by 3. So we've looked at how to convert from the actual score to the z-score, which is the sort of standardized score. And I have another example, the horn honking example, where I have 29 values, a mean of 2.84, a standard deviation of 1.17. Now the numbers aren't as nice anymore, but the idea is the same. If I want to see where does a score of 2 seconds, where does that sit? Well, the mean is 2.84. If I go 2 seconds, if I look at 2 seconds, it sits over here somewhere. So I should get a z-score of -0 point something. If I use the calculation, my x value, the mean standard deviation, I get a z-score of -0.72, which fits with what I expect it to be. So it just tells me, regardless of the numbers, I'm a little under 1 standard deviation step below the mean. Raw score of 4.5 would put me somewhere over here, and I do get a z-score of roughly 1.5. A raw score of 6 seconds puts me way out here, 2.7. 2.7 standard deviation steps above the mean, indicating that that is not going to happen very often at all. Once I go past 2 standard deviation steps to 3, and beyond, that almost never happens. So it's a very, very rare value, very rare score to get. Now, how do I go backwards? Let's go back to my leadership test example. How do I go backwards? Well, the formula is Z equal to X minus the mean over the standard deviation. That is if I'm given the X value and I want to find the Z score. What if I have the reverse? Given a Z score, what is the corresponding raw score value? So I just have to shuffle these things around a little bit. So from this I can multiply both sides by the standard deviation to get X minus the mean equal to, make sure I write it the right way, equal to Z times the standard deviation. Just multiplying both sides. And then add the mean on both sides to get that formula over there. So if I want to go the other way, if I'm given the Z score, I want to find what is the actual score that corresponds to that. It's just a reordering of this formula, like this. So it's up to you if you want to memorize that. I just memorized this one and just reshuffle things to get it in the other arrangement, so to speak. So if I have a Z score of 0, that's 0 times 0 standard deviation steps from the mean, and I'll just get the mean value, which is 20. If I look at a Z score of 1, that is 1 standard deviation step away from the mean, so add it to the mean to give me a score of 23. A Z score of -1, so I take 3 away from the mean to give me a 17. So I can go in either direction. I can get a score value, what is the Z score, or the other, the reverse direction. Let's look at the next example.
Could you go back for a second?
Sure. Where am I now? There.
So you're saying when the Z score is 0, I don't know, I get it.
0 should be on the mean.
Okay.
So the formula should give me back the mean of 20, which it does.
Okay.
Because a Z score of 0 means I'm not moving from it. So I should get the mean back. For the planning ability distribution, mean is 90, standard deviation is 12. If I use this again, now given a Z score of, let's say, -0.5, I know from the previous discussion I should get an 84 back. So I take half a step of the standard deviation less than the mean, which gives me my 84. And I can do any other Z score, and I get the corresponding raw score from that. So I can go in either direction. I have two things that are related to each other. The actual score, X, is related to the Z score. It's just a conversion between the two. It's just sort of a normalization, standardizing the score. Alrighty, horn honking example. Same thing. Even though the numbers are less pleasant, it's the same thing. Given whatever Z score, convert it back to the actual value. Yes, it is. So just to review, let me go back to the distribution shape here. Just to review, if I'm looking at the normal distribution, the bell shape, with the Z scores, the 0 Z value is on the mean. The standard deviation, well, this measures standard deviation steps, so the standard deviation is going to be 1 in terms of the Z score. That's the standardized version. So in that way, I can compare different actual values by standardizing them first, counting how many standard deviation steps I'm away from the mean, telling me when a score is good or better than another score by simply comparing the Z values. And all of this might not seem very practical yet, but visualizing the normal curve with its sections and the Z scores and so on will make my life very much easier when we get to next week and tomorrow actually. All right. So what we have and what I want to remember is these little sections, and adding them together would give me rough ideas of the proportions between the scores. So to specify a normal curve, I would just need to know the mean and the standard deviation to essentially give me how wide this Z value of 1, how much is that in terms of my actual scores, and where is this located? Where is the Z0 value? Okay. So if I've asked my different example questions with percentages falling between different Z values, if I have other values in question, for example, what percentage of scores fall below, let's say, or below is fine. Let's start with above, just to make it simple. What percentage of scores fall above? I don't pick 0, 1, 2, or 3, but what if I pick 1.5? Let's say Z equals 1.5. Now I can't use my 34-14-2 rule and expect my answer to be very accurate. What about a Z value of 1.67? I don't know. I have a very limited set of numbers here to work with. They do give me an idea of where I am. For example, if I look at these numbers, it's putting me somewhere over here. So if I'm looking at the percentage that falls above that, I'm visualizing the area that I'm looking for as, okay, that's 0, that's 1, that's 2, that's 3. I'm looking for something over here. I'm looking for this area. But all I know is these little blocks. I can't say exactly. But a guess would be maybe a little portion of the 14 plus the 2. Now I don't know what portion, it's not just a half, but I can say, oh, maybe roughly a half or a little under a half. So I could take half of 14% plus the 2 to 3 portion and get roughly 9%. So I don't expect my 9% guess to be very close, and these two won't have the same answer, but my guess for them would be the same. Just giving me an idea. I'm looking in this region for an answer. If my answer is like 30%, then I'm a little suspicious. Maybe I did something wrong. Either my guess was way off because I didn't have the right diagram, or my calculation was off. So when I do have more exact Z values that don't fall among the common ones, you'd have to use the exact equation for this. But that is extremely tedious, especially to do by hand. So we can use tables of values that have already been calculated for me to help me find the answers for any other kinds of Z values. So the table is in the back of your textbook as well. That contains the whole thing across, I think, 3 pages. These are just some of them. So it's given in 2 different ways. So for every Z value, I have 2 kinds of percentages. I have the percentage, like the one we're interested in, given a Z value, what percentage falls above that line. And the other one that could be of interest is from the mean to a Z value. What percentage would that be? So in our case, let's look at 1.5. I'm looking for a Z value of 1.5. Now it's not in my table, of course it isn't. But I can look in my textbook, and that'll be on. I didn't want to show the whole thing over slides, just a couple of them. Where would that be in the textbook?
675.
673 is this one, roughly, or some of these. These are on 673. It goes to 674, 675, 676, and that covers the Z values that we need. So for a Z of 1.5, I would look on page 675. Now I scroll down and see 1.5. It's reasonably high up on that table. And I'm looking for the second number because my diagram that I made corresponds to this one. So I'm looking for the percentage in what we call the tail. And I get 6.68. Does everyone see the 6.68? So the percentage is 6.68%. So my guess, I'm perfectly happy with that. I'm not expecting my guess to get very close, but it is in the right vicinity. I didn't get something that's drastically different. 14, half of 14 wasn't very good, but it was good enough to put me in the range of maybe something below 10 is what I'm looking for. That is the exact number. Does that sort of make sense? So if it's not Z, 0, 1, 2, 3, and those guys, then I would have to use a table to get the exact percentage that separates it into 2 pieces. Let's see what else.
Excuse me?
Yes.
When we're using this, and if you were asking for a negative,
Yeah, so I want to do enough examples now to see all the variations.
okay.
And I think I'm doing some of them here. So let's look at this slide and then see which other ones we need to fill it up with. Because I think if I answer your question, I'm going to duplicate this slide.
Okay.
So, what are the steps? Well, this is just a guideline. You don't have to follow them religiously. But it will get me there if I want to have some structure and some steps. So, I'm beginning with a score, either the Z score already or a score, an actual score. And then I would have to convert it to a Z score. Because the table only shows me the Z scores, which is the benefit of standardizing the distribution. Any scores you come across, as long as it follows the normal curve, I standardize it and I really only need this one table. regardless of the scores. Heights of people, IQ scores, everything can be standardized, and I only need this one table. Then, what I find extremely helpful is to make a picture, some sort of diagram indicating what I'm looking for. Shading in the region that I'm looking for, like this. So that you have a nice picture in your head of what you're trying to find. Then, it's really a good idea. People just, it doesn't occur to people to do that step 3. But using my 34, 14, and 2 rule, they add a 50 because it splits it into two 50s. Make a guess of what do I think the answer is going to be roughly. I know it's not going to be exact, but it puts me in the right area, the right range of numbers, so that I have something to compare my exact answer to. Then I want to find the exact percentage using my table, usually, unless it's a very simple z value. And then compare that. Think about your answer. Think about the exact number you're getting and how it compares to your rough guess. Are they sort of in the same range? Are they drastically different? If they're drastically different, then one of the two is not right. One of the two is not right. So you have to have some sort of way to check your answer. So, just check which question this is. What slide is this? 3.7. So, the answer is already on this diagram, but the question is, what is the percentage that fall above a score of 125? So these, I think, are, it doesn't really matter where the actual scores come from. I think this IQ scores. So now the IQ of people in the country has a normal distribution with, mean 100 and standard deviation 15. So that specifies the normal curve. Centered at 100, every standard deviation step is 15 points on the IQ score. What is the percentage, or how many people fall above, I have lost the ability to spell, score of 125? That's the question. How do I get that 4.75? You would want, that's the exact answer eventually. Or let's check that it is. Maybe I'm suspicious. How do you get that? So I would make my diagram, visualizing the area that I'm looking for. There's a 125 line between 115 and 130. So I make steps of the standard deviation. That's what I'm looking for, that area. What percentage does that area cover? So I have to convert that to my z-score. So how do I do that? I take the actual value minus the mean divided by the standard deviation. So in this case, it would be 125 minus 100 over 15, and I get the 1.67. Now I have to look up in my table, where is 1.67? So that should be on page 675. 1.67, sort of halfway down in the first column. 4.75, because I'm looking at the tail. And I get percentage is 4.75. You might be so excited, yeah, it's easy. I don't need to do step 3. But if we do step 3, what would our guess be? What would our guess be? Well, this bit is 14%. It'll be similar to what we just did. This bit is, sorry, 34%, 14, and a 2. So a little bit of 14, maybe half. I know it's less, but it doesn't matter. Half of 14 plus a 2. So my guess would be roughly half of 14. I don't have to worry about other kinds of fractions. I'm just trying to get to the right size number. Plus the other 2%. So I would guess less than 9%. So it seems it doesn't have to be close, but it puts me in the right area, in the right range of numbers. Okay, what else can we do? We can ask something like this, where I'm still using IQ scores, mean 100, standard deviation 115. How many fall above a score of 95? Now I know that, I leave this, so the question is above a score of 95. So I know that the average is 100, so over half of the population will be will have a score of 95 or above. So I can break it up into little pieces. There's my halfway line. There's my 95. I know this guy is 50%. I really only need to worry about this guy. We do it in little sections. So, let's convert this to a z-score first. What is the z-score going to be? How do I find that negative 0.33? Well, 95 minus 100 over 15. 95 is less than 100, so that's where I get a negative 0.33. Negative 0.33. Sorry, let me write that down. 95 minus 100 over 15. So I need the z-score to use the table. So it's standardized, so there's only one table for any set of scores. So now in the table, let me just go up to what the table looks like. Because of symmetry, the table only gives me areas on the right of the halfway line at the mean. So if I find this little area, it's the same as this one. On the left side of the mean or the right side of the mean. It's the same area because of the symmetry. So it doesn't have to give me any areas, any negative numbers, any negative z numbers, z scores. Because of symmetry, it's exactly the same. So what am I going to look for in my table? Which z value am I going to look for? If my actual z score is negative 0.33, there's no negative 0.33 here. What am I going to look for? 0.33. So instead of finding this, it's the same. This little area is the same as, there's my halfway line, it's the same as this area. So I just look at the other side of it. So that is going to be a 0.33 and a 0. Because of the symmetry. Like this cuts it in half exactly, so it's sort of, if I fold it on this 0 line, it's exactly the same. So I'm going to look for a z score of 0.33. That will be on page 673. Second column. Is it on here? No, it's sadly not. 0.33, and now I'm going to look at this one. We're going to look for this one, not the tail. The percentage mean to the z-score. 0.33, what do I get?
$12.93.
12.93. So this is 12.93%, which means this is 12.93%. Everyone happy with this symmetry? So it just makes it easier that the table doesn't have to show all the z values. In fact, it doesn't show any negative z values. So I have to just see what I want and then sort of transfer it to be able to use the table and then go back. And all the percentages are there. So, I erase this. What was the question? Above this 95 line or above a z-score of negative 0.33. So then the answer will be 12.93% plus the 50% of that second half will give me 62.93%. Is that what I would guess? Is that what I would guess? Well, where does this z-score put me? It puts me inside this -1 to 0 region. So you could guess, just for simplicity, half of that, half of 34%, plus the whole second half, which is 50. What is this? 17 plus 50, 67%, and it's very close. I'm not expecting it to be very close, but it puts me in the right range of numbers. Now, what did their answer show? It's not quite right, is it? Sadly, this slide came from the book, and that's not quite right. So just make a note that in the slides, that is the right number. Not this one. Not this one. Not sure why they would do that, because they have the 12.93 here. Just add it to 50, it's right there. It's a little silly typo. It happens now and then, I see it. So just when you look at that, don't get confused. How on earth are we getting 62.17? Makes no sense. It doesn't make sense to me, right? Because it's wrong. Okay, so I think there is more to do in the way of an example. It doesn't quite cover what you asked, I don't think. So let's look at what else can we ask? We have the time. You could cover all the possibilities. So, but when you look at the question on your own, you don't get stuck. You want a reference, an example to work from. So let's stick to the IQ examples. IQ has a mean of 100, standard deviation of 15. And let's just pick a score. So I want to do two examples. What is the percentage of people that fall below, let's say, I don't know, 80? People that fall below 80. So now I want to visualize what I'm doing. What is the region that I'm looking for? Well, my center line is the mean, that's at 100. 15 is my standard deviation step size. So if I step one to the left, that would put me at 85. Another one to the left will put me at 70. So my 80 is somewhere over here. I don't really care, just somewhere in between. I don't want to put it too close because then it looks bad. So I'm looking for the percentage below that. So I'm looking for that region. So next is, this is my x. What is the corresponding z-score? So it'll be 80 minus 100 over 15. So that's negative 20 over 15. And what is the number that I get there? That's why we should have a calculator now and then to use with little things like this. So 2 decimal places are fine. The table shows 2 decimal places as well. What is the number that I get?
1.33.
1.33.
Or negative.
Negative. All right. So now, if I just wanted to guess, what should this be? Well, this one is 34%. This whole section here is 14%. And that is at 2%. So I would guess more or less 7% plus 2%. A little half or a portion of the 14 plus the 2, 9%. I don't care about the fraction changing. I just take half of it. I know it's not right, but it puts me in the right range of numbers. Now the exact answer. Well, now I have to go look. Which one of these two am I going to use? This one or this one? Left or right?
Right.
Right. So whether this is on the left or the right tail, it doesn't matter because the symmetry is the same. So on the other side, there is a z value, a z score of 1.33. And this region over here is the same as this one. Everyone happy with that? It's the same. So I use my table. It's probably not in the slide. 1.33 is on page 674. 1.33, the second number 9.18. Wow, my guess was pretty good. 9.18%. 9.18%. Oh, good guess. I don't expect to be super close. In this case I was, in the other example I wasn't. Should we do another example? Is there one you're not sure about, or does that cover them all? I feel that covers them all, but let me know if you think of something that you're not quite sure about. Any questions on this? So identifying the standard, the normal distribution as the one in question here, because it's a theoretical distribution, everything has been figured out. And I can use that to my advantage.
Maybe we could do one that's between.
Between, absolutely. The nice thing about how the table is set up is that this first column, or the middle column, helps me with that fairly easily. Do you want to come up with an example? Yours is as good as mine, it doesn't matter.
We could say percentage, so you want me to say the raw score?
The IQ values.
Okay, so percentage between 85.
85 is too nice. Do 7.
87, okay. And 24. 124.
124, yeah, that's a good one. All right, 24. Hopefully no one has an IQ of 24. That would be so rare you can almost not even measure it.
I don't think that would be a function.
No, probably not. No. Yeah, you can't measure it if they're not able to take the test.
Yeah.
Right. Good point. So there are limits. Yes.
Break it.
All right, so now visualize. And in other classes, I've said so many times, visualize the region. Well, they don't listen. I'm just going to go calculate stuff. And what happens? They get it wrong. Why? Because you didn't follow the steps. The steps are there to help me. Okay, so I have the center here is at 100. So I'll just mark it off. This sort of exaggerated a little bit. 85 is my next cutoff. I'll do that sort of dotted lines, and I don't need to worry about anything below that, so my line sits over here at 87. On the one side, on the other side I have 115, and the next one will be 130, so 124 sits over here. 124, so I'm going to change the color to be red. So I'm looking for all of that. So what would I guess? I'll leave some space here. Okay. What would I guess? Oh, this little bit is 34%. This bit is 34. This whole one is 14%. I don't really care because it's just a guess. I don't really care about making changing the fractions. So I'm just going to take half of 34%, then add this 34%, and then add half of the 14% region. I know it's not exactly a half, but I don't need to be accurate with my guess. Just getting me into the right area. 17 plus 34 is 51, plus another 7, so it looks like roughly 58%. I don't know how close I'm actually going to get, but it puts me in the 50-60 range. So if I get something that's drastically different than that, let me just rethink this a little bit. So let's call this x1 and x2. So then my first z-score is going to be 87 minus 100 over 15. And my second z-score is going to be 124 minus 100 over 15. Now, I don't have a calculator with me, so you guys let me know. What is the Z1 score rounded to the nearest 2 decimal places? So there are some steps involved here, but when you do it a few times, I don't think it's too complicated at all. And a lot of what we're doing later on relies on this visualization of the regions, having a certain cutoff, looking at the left and the right side. It'll be very beneficial later on. Who has a number for the first Z value?
Negative 0.86.
And the other one?
Wouldn't it be 0.87?
Yep.
Oh,
What is it
you're right.
exactly?
0.866.
Yes, 10.7. Now, I'm not going to be too uptight about which one you pick, so I'll give some flexibility there. But as long as you pick one of those two. What about this one? It'll be 1 point something.
1.60.
1.60. Okay, so now I want to come up with a strategy for how am I going to use the table with this. So let me use another color. Purple, sure. That I'm going to find the red percentage. And then we'll find the purple percentage. Because the table can get me from the mean to a z-score. So mean to a z-score, mean to a z-score. And then I'll add them together. So let's do the red one first. What is the z-score that I'll look up in the table?
I'm doing something.
0.87. 0.87 is on page 674. 0.87, I'm looking at the middle, the percentage mean to z. 0.87, 30.78. All right. Then for the purple one, I'm going to use 1.6, which is on page 675, 1.6, 4452. Okay, percent. My guess was way off. Add them together and I get 75.3%. Now, yes, my guess was pretty far off because these guys were so close to the edges of those regions, the half was not really very good. But it puts me in the 60 range, so I'm not going to get too alarmed by that. I would get alarmed if I get like 20% or something, and something went wrong. Just a guess, putting me in the right area.
Wait, so it means something went wrong?
If my guess is drastically different than my calculation, one of them's wrong.
Oh.
Either my guess is, I didn't guess correctly in terms of using the 34.422,
Yeah,
or something went wrong here. Either way, I need to recheck.
okay,
They need to at least agree, sort of.
okay.
Because what people do is they just calculate this, they don't look at this number, don't see if it makes sense or anything. I just want to do that check. Does this make sense? This is the majority of the region, because I have little 2 pieces here, and then 14 here. Yeah, 75. Seems okay.
Could you do it the other way where you calculate the tail and subtract that from 100?
Yeah, you totally could. We could totally have said, does this green work? We could totally have said, let's calculate the tail here and the tail there and take it away from 100. So when I sort of try and see if this number is realistic to expect, I see, well, how much am I not including? A little 2% here, a little 14 and 2% here. Yeah, that seems okay. So it's just good to just think about what this is saying, and does it match what my intuition tells me according to the 34, 14, and 2 rule. I might not be able to guess it exactly, but that's close enough.
Okay,
Okay,
a
that
big
covers.
thing with the comparing your guess and your final answer thing would be like, if your guess was like 58% and your final answer was like 20%.
Then there's some alarm bells.
Because
Yes.
you would know, because 20% is less than an entire section that you're
Yeah,
going to
something
have
went wrong.
to take up.
Yeah. And you can totally adjust this. You can say, oh, this guy is the majority of this 34%. So let's change the fraction to something else. And this guy sits close to the 130, so I don't want to take just half of the 14, I'll take most of it. But I don't really bother, it's just a guess. It's not worth my time and effort here. Just a portion of that region, the full region here, a portion of that will put me close enough. Okay, so that was 3.7. Should we take a break or do the last example where we go the reverse direction? Given a percentage, what is the score? So we've done the one direction where given an actual or a z-score, what is the percentages involved, either contained between two z-score or two z-scores or the tail from one z-score. The other one is then, of course, given a percentage, let's suppose, given that I'm looking at the top 2%, what is the score that would sort of separate the top 2% from the other 98%? Now, if I use the top 2%, then obviously the z-score is 2. If I say, oh, the top 16%, what is the score that separates the top 16% from the bottom 84%? That would be a z-score of 1. So that's tied to the idea of percentiles, where I have a cutoff breaking it up into 2 regions under the curve. So if I look at the 98th percentile, it's the score that separates the population into the bottom 98% and the top 2%. The z-score of 1, roughly speaking, will be the 84th percentile, because 84% fall below that, 16% above that. What would be the 16th percentile? 16th percentile, separating it 16% below and the rest above. 50th percentile, 50 below, 50 above. So the question now is linked to the idea of percentiles. Given the percentage, what is the score? So for that, the steps are similar. I want to just visualize what I'm given, what I'm trying to find. Where do I expect it to sit using the 34, 14, and 2 rule of thumb? And then make a rough guess. What do I think the z-score should be? Then I can use the table to find the exact z-score related back to the actual score, if I'm given that. So let's see, let's just make some examples. If I stick to, I don't want to do that one just yet. If I stick to the IQ example with a mean of 100, standard deviation of 15, and I could ask, I can phrase the question in many ways. What is find the score, the IQ score, that, thinking of the best way to phrase this, without using the word percentile, because that's exactly what a percentile is. Let's say, find the score for which 40% of the population, find the score for which 40% of the population fall below that score, or whatever. Grammar aside, does everyone understand the question? There's so many ways to phrase it. I would like to phrase it in terms of percentiles, but I just don't want to do that in the very first example. But that's exactly what a percentile is. I'm looking for the score that breaks it up into 40% below, and then the rest above. What is this score? Well, let me just break it up according to the ones that I do know. 100. Now I know 50% will be below 100. If that's my cutoff, that's too big. If I use a cutoff of 85, which is one standard deviation step to the left, then over here will be, well, I don't remember, maybe let's go back. It will be 16% below. So that tells me that 50% below, if I start at 100, 16% below if I start at 85. I'm looking for 40, so it's going to be between these two. Everyone happy that it's between those two? All right. What is the score? Now, so my guess really, my guess is then just going to be, it's between these two because 40 is closer to 50 than it is to 16. I'm guessing it's going to be just under IQ score of 100. It's not going to be 100, it's going to be under 100, but not by that much. Now let's see what exactly is it. So I'm looking for this region to be 40%. 40%. Find the z-score first. So let's say here from table. And now I have to use the table in reverse. Let's go back to the table picture for a second. Which column am I going to use? The left one or the right one? Which picture am I going to use? The right one. Even though it sits on that side, it doesn't really matter. I can make a purple over here and look at the one that's 40 on that side. Fold it over through this line and it's going to be exactly the same. So I'm going to look at the right hand picture and I'm going to look now in the percentage column when I get a 40 and then find the corresponding Z value. So I'm using the table in reverse. Is that maybe on my, no, it's not on this side, but it's close. It's going to be over here somewhere. So where is that exactly? It should be on page 673. So now I go in this column and I go down looking for a 40. 40, 40, 40. It's not quite there. It's not quite there. I find Z and the percentage. I find 40.13, and that corresponds to Z score of 0.25. And the next one jumps over the 40, 39.74, and that will be a Z score of 0.26. Now,
I'm so confused now.
all right. We're using it in reverse because previously we were given a Z score, find the percentage.
Yeah.
Now we're given a percentage, find the Z score.
So just find the corresponding 40% value.
So now I have, it's like I have the answer. What is the question?
I
So
think
I
I have
have
an
to-
older textbook, so I can't really follow with your page number, so now I can't.
Do you have, it's the first, do you have these guys still?
It's on page 670.
Oh, okay,
The start of the table.
Well, I'm
You
looking
see
at the
this?
back of the book. So it's just 40.13.
These two.
Okay, thanks.
The table, it should show the same. It's just
Yeah.
a question of where.
Okay, thank you.
So now I find these and my answer sits between them. Now, different books do different things. One book could say, or one argument could say, we're just getting an idea, getting as close as possible. We will pick the closest number, which would then be 40.13. I prefer to just average these two out and pick the number in between, because 40 sits pretty much in between. So I would prefer, I'll accept both, I would prefer to take the average of those two numbers. You don't have to actually calculate it, just halfway, which would be 0.255. But anything in this range, I'll accept. We want to get as close as possible. These are pretty much the same distance away. You can get even more technical, so I don't want to do that. You either pick the closest one or pick the halfway point, just for simplicity. So if you pick, well, the closest one is 0.25, that's okay as well. But I think at the very least we can just go halfway between them. We can get fancier, but I don't want to. Okay, so that's one example. That's not quite finished. I want the IQ score that corresponds to this. So the x value that corresponds to this, what was that? The z value times the standard deviation plus the mean. So let's pick 0.255 times 15 plus 100, and what do I get? There's some calculation involved. I can't write as much as I'd like to because I only have this little board space. This little bit.
103.825.
Sorry, what?
103.825.
Does that seem right? What did we do?
You said, it's to the left of the mean, so
So was this actually my z-score? That's the one that comes from the table. What is the one I'm interested in? It's just the negative of that. See how easy it is to make a mistake? I totally did this on purpose to point out how easy it is to just forget a little negative. So with that in mind, the z-score that I want, according to my diagram, which emphasizes why it's so important to visualize what's happening, is negative 0.255. Just off 0, just to the left of 0. So what do I get then? 92? 96. 0.18. I don't really care how many decimals you have for an IQ score. Doesn't really matter. Which does agree with what I suspect. I suspected that it's just under 100. So even though you might have forgotten that negative, I immediately knew, no, there's no way it's above 100. I'm looking for something just under 100. I don't know exactly by how much, but I know it's just under 100. So this one feels much better. Yes?
I understand the later part of what you're doing, but I'm confused when you were talking about like how there's a part that's under 16%, right? And like just basically how you found that 40% and you knew.
So the 40% is given. That's in the question.
Yes, but
Now my guess, you mean?
Knowing where it was on the normal curve, because you said how there's a certain part that's 16%. I understand that because that's 14 plus 2.
Yeah, so the 100%, that's 100%. The 100 IQ is the middle value. So 50% on the left, 50% on the right. Now I'm looking for the line that gives me 40%. So I just have to move a little bit from 100 to have 40 on the left. Because if I'm at 100, then it's 50, that's too much.
Okay.
So move a little bit to the left, shrink that 50 a little bit to 40. So I'm just going to move a little bit over here. And then I'll have 40 on the left. The question is, how much do I move?
Oh, okay.
So the first step, the first major step is to know where it puts me, where the percentage puts me on the score horizontal line.
So I don't need to think about that 34% in that? I think that's what basically.
I do and I don't. In this case, you don't have to, because clearly 40 is not going to be taking me very far from the 100.
Okay.
But I also want to check how many standard deviation steps do I jump to the left. Do I move so far to the left that I'm crossing over this line to this region? No, because if I'm crossing over the -1 line, then I only have 16% on the left, and I want 40, so I'm not going to get close to this line. I'm just going to be over here.
Okay, okay.
But if the 40 instead was a 12, then I would have to move into this region
Okay,
before I have 12 on the left,
yeah.
which will give me a better indication of the z-score I'm looking for.
Okay.
So you don't really need it, but in order for me to have a fairly good guess, I want to know which region I'm in. So that,
Okay.
do I expect a z-score of negative 0 point something, or do I expect a z-score of negative 1 point something? Then at least I know what to expect.
Okay.
And it's just the something that I'm looking for.
Yeah.
So it helps me to guess a little more accurately. Okay, so this is exactly what a percentile is. So I could also ask, find the 90th percentile. So that means, what is the IQ score? If someone takes an IQ test, which apparently they don't do that anymore. I don't know why. Well, many people have said, no, they don't do that anymore. So who knows? But if you take whatever test with a result, and the results come back and say, oh, you're in the 90th percentile. What does that mean? What does that mean? What does that imply? That implies that this is where you are, there you are. Maybe you have long hair. There you are. You scored fairly well. They say you're in the 90th percentile. That means that 90% of the people are below you and 10% are above you, or you're in the top 10%. What is that cutoff line? So it's the same question. Okay, so now I want to know what is this score that leaves 10% at the top and 90% at the bottom. Well, if I just have a guess first, I want to put myself in the right region to at least know what kind of z-score I'm looking for. I don't know the decimals, but at least I'll get it fairly accurately. So here is my 100 line, separating into 50-50, that's not even close. Here is the next standard deviation step. So then, if I'm at this point, how much is to the right of me, roughly? Well, it puts me over here. I still have 16% above me. And I'm looking for 10. So maybe this 10 should just be shifted a little bit. I'm over here. So the 10% is above me. The next standard deviation step is going to be 130, and only 2% of the population is above that. Only 2%. So I'm not going to go that far. So I'm in between Z0, 1, 2. I'm in between the 1 and the 2 Z score values. Does that make sense? So it just helps me make a better guess. Now I don't know, how close am I? Am I closer to the 2 than to the 1? Nah, I'm somewhere in between, and that's a good enough guess. Somewhere in between. Okay, so now I want to know, what is it exactly? What is it exactly? So now I have to look at my table. Now I'm looking for that region, so the table will be fairly easy to read. I'm looking for the same tail that the table shows, so the right and one of the two, this one. And I'm going to search for a Z value of 1. Which is? What number am I going
Those
to
are 10.
hope to see? I'm looking for a 10 here. It's exactly, it matches up exactly to what I have, so that's the easy version. Now I'm looking percentage in the tail, 10, now I'm going to have to turn the page. 10, 10, 10, I have it on 674. I don't expect to see it exactly close. Let me say what I have here. I see a 10.03, 1.28, and I also see a 9.85, 1.29. Now, I'm going to leave it up to you, to be honest. Because the actual way to find the Z value in between, I don't want us to do because it'll just confuse us. I'll leave it up to you. Either pick the closest one or pick the middle value. In this case, the 10.03 is obviously the closer one. So I would just pick 1.28. The previous example had it pretty much in the middle. Then you can either still pick the closest one or pick the halfway point. So do whichever one feels good to you. I'll accept both. So we can take the Z score of 1.28. I think that puts us close enough. It's okay. So this will be 1.28, which fits with what I expected. I expect to get something between 1 and 2. You could have argued further to say, oh, 10% puts me a little closer to the 1 than to the 2, so I'm expecting to be a little closer to 1 than to 2, and that lines up as well. Now I want to find the corresponding IQ score. So the IQ score that corresponds to this will be my Z value times my standard deviation plus the mean. So it'll be 1.28 times 15 plus 100. What do I get? 119.2, 119.2. And that again fits with something that falls between 115 and 130. So that means that if you score on the IQ test 119, more or less, then you're in the top 90% of the population. So it's good to understand the idea of percentiles. It's really just, I like to think they came up with the idea of percentiles so that I don't have to get caught up in unpleasant grammar sentences trying to explain this very concept. So we call it a percentile because that's exactly the line, the point, that breaks it up into certain percentages. Any question on this one? This I feel is the basic one because the table shows exactly what I have. I don't have to flip it, I don't have to do anything. Any questions on that?
So to be in the 90th percentile,
You have to have an IQ, let's say 119 or more.
or more, okay.
I don't know how high that actually is. I asked the class once, or usually every time I do it, I ask the class, do you know your IQ? And then many people said at one point, no, they don't do that anymore. So I guess they phased it out for some reason. I mean, it is a little bit subjective in my experience that depending on when you take the test, you get different scores. But I don't know how well it actually, I don't know if you can really measure intelligence correctly.
It's kind of gone the way of knowing your blood type. Like there's no, in like high school curriculum,
Yeah.
so if you don't actually do that in a science course anymore.
Yeah.
Knowing your blood phenotype, and likewise, you don't really encounter an
Yeah.
official IQ test.
Yeah, and I think in some situations it's a little unfair to put a number on it because there are different kinds of intelligence. You know. But it's interesting, yeah. But probably not the best way to measure a person's ability. Yeah. All right. Any other questions on this? So again, the steps. Visualize. Or we can do their example. Visualize what's happening. And by not doing this first step, you're really putting yourself at a disadvantage, which just makes it a little more risky. It's not that you can't do it. It's not that I have to see this. You're just playing it safe because you want to get to the answer. Then just have a rough idea of what z-score am I looking at. Then find it using the table in reverse and get back to the actual score. So the example here is worth doing, I think. And then we're done with this chapter. So this chapter is all about getting used to the normal curve and the proportions and what it means with the score and the percentage. And that really makes my life much easier when I go to the following chapters, because being able to visualize this is going to make things much easier. So there, what do they have? Still IQ score example. So they want to look at what IQ score separates the population into 45 below, 55% above. So given the 55%, and I'm trying to find what is the score? What is the score? So it's visualized there, so I don't have to do that. But because I'm given 55, I know it's just off the halfway point, just off the 100 IQ. By how much? By a little 5%. Little 5% more than the halfway line would be. So my line, my point is going to sit right there, so that this is 5%, which is how I'm going to use the table. So now I'm looking for this column, and I want to see a 5%. Is it actually on my slide? Yes. So it's the percentage from the mean. So I look for a 5%, 4.78, which has a z-score of 0.12. And the other one that I should consider is 5.17, putting me at a z-score of 0.13. So in this case, I feel that this is pretty much in the middle. So I'll pick a z-score that's in between the two. So we can take a z-score of, halfway between them is 0.125. Is it positive or negative? Negative is to the left, so I simply put the negative in. The table is not going to show that, but if I visualize it, it's going to be to the left of the mean, so negative. So then, the corresponding IQ score that has 55% of the population above it will be negative 0.125 times the standard deviation of 15 plus the mean. What do I get? Should be something just under 100. Oh, all right. Let's just verify what they do, because we've seen that it's not always completely accurate. Is it 98.05? Let's just check. It does seem right, but I'm not sure about the decimal.
I bet you they didn't round off the z-score.
I got 98.13.
Yeah, it does depend on how you do this. Fair enough. 98.13. And like I said, there is a more exact way to do it, but I don't want to get into interpolation techniques here. So you can either pick the closest one, but sometimes which one's closer? This one. I prefer, if they're that sort of balanced, pick the one in the middle, will be more accurate. But I'll accept either one, doesn't matter. If there's a clear winner here by a couple of decimals, then I'll pick that one. But it gets me close enough. Close enough. All right, any questions on that? I lied a little, we're not done with the chapter, but for the most part, that is the main part of the chapter finished. Just a little bit more to say regarding the idea of a sample versus the population. And as we go ahead to inferential statistics, that's really the key idea. Sample versus population. I'm not going to write too much on the board, and the slides don't say too much. We're just discussing it, and then you can read more in the textbook. The population is what I call the set of all possible individuals. Let's imagine people with IQ scores. The population is the the collection of IQ scores of everyone. Everyone. When I just test a few people, I can test everyone in this room. That's not all people. It's just a sample of people. So a sample is a subset, a smaller collection from the whole population. If their analogy is you have the pot of beans, there's the whole population. All the beans are in here. If you take a little spoonful, that's only a sample of the beans, not all the beans. So the idea of inferential statistics is you have your whole pot of beans, you take a spoonful, you taste it. If it tastes good, you conclude that the whole pot of beans will be good. But you don't know for sure. You're basing it on your sample. Or you can have sort of a diagram, circle containing all possible, the whole region is contained inside the circle. If I then look at a smaller little region inside, that's only a sample. It doesn't look at everything. Yeah, I'm not a fan of this example too much, but if you have a histogram where you considered everyone, the little black dots could be the frequencies that you get from a smaller collection of those, of that population. I like the bean. It's cute. I never would have thought of that. So there are different ways to sample, to make a sample. You can stir the pot of beans and just randomly take a spoonful. You cannot. That's maybe a good random sample. You can do what they call a haphazard selection, where maybe I don't stir the beans, and I just take a spoonful from the edge. Well, maybe those beans are a little bit better than the middle ones. Maybe the heat didn't spread exactly evenly throughout. So I have to be careful about how I make my sample. I want my sample to be representative of the whole population. So if I just turn on the heat and wait a little bit, where I take my spoon is going to be giving me a false impression of the population, perhaps. So for example, if I take look at the IQ score example, I have to be careful. I can't necessarily take the IQ scores of everyone in this class and then use that to draw conclusions for the whole population, because we're not necessarily representative of the whole population. So I have to be careful in that sense, especially when I'm planning a research project that the sample that I investigate should be, as much as possible, representative of the whole population. Another couple of examples, if I look at all Canadian women, for example, and I just take a sample, whatever I'm measuring, IQ test, height, whatever. My sample, when I look at the frequencies in the histogram, is not going to exactly correspond to the population's frequency, the population distribution. But if I have a good representative sample, then it's going to be close. And the larger my sample, the closer it'll get. But I'm sort of limited due to practical reasons in how big my sample can be sometimes. The ideal is that I go and survey all Canadian women, but that's not practical. We want our sample, we're going to look at our sample, it's manageable, but we also want that to be representative of what's actually happening. If we look at voting, taking a poll for all the voters, you can't ask every single voter what they did or what they're going to do. You sort of take a poll and let your sample suggest what the whole population is actually doing. Any questions on the idea of sample versus population? Sample, population. Spoonful, whole pot of beans. And that's the key idea leading into the next chapter. Now, to be perfectly honest, before I say that, when we get to the mean, standard deviation, variance, we want the symbols to have different names so that they immediately indicate whether I'm talking about the whole population or the sample statistic value, the sample. So the names that we've used up to this point, we're going to reserve for when we talk about the sample value. So I have a sample of IQ value, sample of people that I've surveyed. The average value, the standard deviation, the variance, I'll call that. And the convention is when I talk about the whole population, then I use Greek letters to represent the mean, mu for the mean, sigma for the standard deviation, and because the standard deviation squared is the variance, I will use sigma squared as the name for the variance. The variance I need to get to the standard deviation, but these first two are the important ones. So when I see a mu and a sigma, that refers to the actual mean and standard deviation of the whole population. When I look at a specific sample of people, then the average value and the standard deviation might not be exactly the same. But I'm hoping that if it's a representative sample, these guys will approximate the actual population parameters. So we use the word parameter for the population, and we use the word statistic for my sample. So population parameter versus, population parameter versus sample statistic. Why is this blue lighter than the other blue? I don't know. Okay, so just some terminology. Now we want to distinguish between when I'm talking about a population and when I'm talking about a sample. And that continues for the rest of our course. Now, I don't want to really talk about probability because we don't need it outside of intuitive understanding of probability. So, when I look at frequencies, I look at how many times something occurs. And when I survey something or I get a result by doing something, we call that result the outcome, and then the frequencies just tell me how many times I got a specific survey result or how many times I got whatever result I'm interested in. If I then look at the percentages like we've done with the frequency table, we can call those relative frequencies. It's the percentage relative to the total number. Whether I look at that as a percentage or a fraction, relative frequency. So that really gives me the idea of probabilities. For example, if I survey people and I get my frequency table, my different variable values, my frequencies and my frequency percentages. If I have different values here, and I get frequencies, oh well, this occurred 5 times, this occurred 6 times, this occurred maybe only once, and then 3 times, and so on, and they add up to 100. Oops, again. 100. So I looked at 100 people in my sample, and I got the different frequencies. Then this occurred with relative frequency of 5%, because it's 5 out of 100, 6 out of 100, 1%, and so on. So this would be 5 out of 100. Then if I were to randomly pick someone from this sample, the probability that their result was a 0 in the survey, I would expect that to be 5%, because 5 out of the 100 people had this score. So the relative frequencies will be an indication of how likely it is to get someone with that outcome, that result. Now, if my sample is representative of the whole population, then I can say, okay, this is representative of what people would do in general. In my sample, I got a relative frequency of 5%, so I can use that and expect that in my whole population, 5% of people will give me a score of 0. So the relative frequencies are approximations of the actual probabilities of what to expect if I randomly select a person. The likelihood of a certain outcome. That's all I want to really say. So if I look at all possible outcomes, all possible people, 100 people, the possible successful outcomes is whatever I focus on. Let's suppose I focus on the 0 result. 5 out of 100 gives me a number that I can measure the likelihood of something. And we call that a probability. If I flip a coin, the chance of getting heads is 1 in 2. So it's 1/2 or 50%. You can go between percentages or the fraction as you wish. If I buy a lottery ticket, out of 1,000,000 tickets, there are 800 winners. The chances of winning something is 800 out of 1,000,000, and so on. So the probability is just a way to measure, by way of a number, how likely something is. I'm going to get to the normal distribution. I don't think I showed it here. Where's my normal curve? There we go. So if this is my histogram, the relative frequencies here will be approximations for what actually happens to the whole population. So in that sense, this is a probability distribution. Yes?
So the probability distribution is like a normal curve.
Yes.
When do normal curves actually happen? Because they're kind of ideal, aren't they?
It's a theoretical ideal, let's say. But if you look at many, many things, if your sample is big enough and and balanced enough, let's say, the histogram will eventually exhibit this bell shape.
And then
And
just
you do it
use the
from
math for normal.
Many different experiments, people kept finding it, kept having this bell shape to it. And then they went and let's come up with an equation that represents this, and depending on the mean and the standard deviation, it adjusts a little bit, shrinks a little bit, but it still has that basic shape. And it comes up all the time, all the time.
And does it always have to be that tall?
The height and everything is going to depend on the mean and standard deviation. Because if the standard deviation is big, this is stretched out, then it will lower a little bit in order to cover more.
But all
If
the
it's narrow, it's
percentages
really
would
higher.
stay the same. But the percentages would all stay the same.
The percentages under that curve is always the same. So when you think about it, it's interesting how so many things, not everything, if you look at the wait times at a lineup for a drive-through or something, it doesn't follow that.
Yeah.
It looks different. But many things have this. And things like the central limit theorem says, avoiding certain words on purpose now, it says informally that if I just look at enough samples, or large enough samples, everything in some sense approaches this normal curve. By just looking at it from the right angle, or in the right way, everything approaches the normal curve. If I just take a sample of us in the class, we're not representative. So our histogram won't look, when you look at our histogram, it won't look like a bell curve, because the sample's not representative. But if you have a big enough sample and it covers the properties of the population, you'll see the shape emerging. So then the benefit of having a theoretical line that estimates the actual probabilities is that you can go and analyze this mathematically and get those percentages and everything. And they're very good estimates of what's actually happening. So you don't have to look at every specific situation. You match it to this, and there are ways to say, yeah, it's a good enough match or not. We'll get to all those. And once you match it, then you can just use all the properties. And you immediately know a lot about your property or your survey or whatever it is, your population. So there are a section on advanced topics in probability. We don't need it, but you're welcome to read it if you want to. I'll leave it as sort of a self-study since we won't be using it directly. That's 4. So the normal curve gives me I can go between these. I can graph a histogram by using the actual frequency numbers or the percentages. And in that sense, the histogram distribution, the frequency distribution is also a probability distribution. And when I look at the whole population, I get the probability distribution that often exhibits this normal curve shape. All right, that is the end of chapter 3.